And we are now recording. Let's go from current slide. Let me make just a couple of announcements. I don't know if they're useful for you or not, but let me just make them. If any of you, or if you know of anyone who's interested in maybe teaching math or science as a profession, there is a program at Alabama A&M. It's called the Noyce Scholarship Program that I don't know all the requirements to do, but if you get selected for it, your last 2 years are basically paid for. Your junior and senior years are paid for. I'm sure there's some stipulations and stuff, but if you are on Lost and Stay email, which I think all of you are, check your email. And it was one probably a couple weeks ago from Alabama A&M, and it's concerning the Noyce Scholarship Program. Sounds like a great program. And if you know of anyone who'd be interested in that, spread the word on that. Now, I don't know if any of you would even have a possibility of coming on a Friday morning to catch me. Last Friday and the next 3 Fridays, my schedule was just really wacko. Last Friday, I needed to make up a test. I had a hematology appointment on Tuesday morning, missed my Math 112 class. I asked them on Thursday when they want to make it up. They could it be Monday morning, Monday or Wednesday morning, or Monday afternoon. They said no, Friday morning. So I made up my class on the Bessemer campus, and I checked with my boss, and he said no reason to go to Birmingham, so I worked out there. Normally I'm on Birmingham West Campus Fridays 8 to 12, and that's on the syllabus and stuff. Well, this Friday I have a dermatology appointment, okay, and that's at 9:15, which is very inconvenient because it's right in the middle of the morning. So I haven't decided. I'll talk with my boss and see what he says, whether I should come in before 8 like I usually do, but then I have to leave by 8:45 to get back to the Kirkland Clinic at 9:15, and then to turn around and go back to the Birmingham campus. And I know I'll be there the last part of the day. I just don't know if I'll be there the first part. But I will be on the Birmingham campus probably from 10:45-ish or so to 11 until I'm through doing everything I need to do there. Okay, so that's this Friday. Next Friday, I'm not going to be on either campus at all because I'm on an articulation committee that's meeting in Mobile. So I have to drive down Friday morning, leave home about 7, drive, from 4 to 5 hours to Mobile, attend a 3-hour meeting, and then drive back another 4 or 5 hours. So
I think you should be here next Wednesday.
Huh? So that's going to be next Friday, okay? Not this Friday, the following Friday. And then the Friday after that, I have an eye appointment at Birmingham, but it's at the Birmingham East Hospital, so I'll go to UAB West Hospital, and so I'll go to the the campus over there, and it's at 8:15, so I'll go there by 8 o'clock like I normally do, go across to the hospital for my appointment, and then find out whether I need to go back here or there, one way or the other. Yes, sir. The second test or the third? Second or third? Yeah, I haven't given the third yet. When you said new test, second. Okay, you need the second test. Okay. All right. We're getting close to the third. Okay. Acceleration. Work done. You also need the second test? Okay. All right. And the other thing I need is to mark the 2 of you present. Once I can find my pen. There it went. Nope. There it went. Okay. Is this Sir Darius? Okay, I thought so. And it's Vontae? Trent, that's right. I need that. Also, we're missing Jasmine Davis and Jasmine Mason. The Jasmines aren't doing well today. And Vontae. Ah, and here's one. Jasmine, huh?
Mason.
Mason. Okay. All right. So now we're just missing Jasmine Davis and Vontae. All right. So that's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Got it. All right. So the third Friday from, this coming Friday, day after tomorrow, the following Friday, the third Friday, I'll have an eye appointment at the Birmingham West Hospital. That won't take, hopefully, so long, and I'll either work on Bessemer or work on, come back to Birmingham after that. And then shortly after that is spring break, and I'm going to be here that Friday at all. Okay. All right. Any questions on anything we've done so far? Yeah, that's when you want to ask a question. Say, okay.
8.2.
Okay, wait a minute. Somehow that got separated out of the book. Okay. Let me find something to hold my place here, so I'll know where to come back to it. 8.3.
I have one from 8.3 and 8.2.
Okay. 8.3. Find it here. Okay. What page is that on?
217 is 8.3.
That was a pretty long chapter, wasn't it? All right. 217. Found it.
Number 3.
Number 3. All right. This is page 217. Whoop, let me get my pen set up. This is problem set 8.3 and number 3. All right. They don't give you much except they just start with this. M, standing for mass, of course, is equal to 4.70 kilograms. Of course, that means 3 significant digits. And why did that disappear? Okay, there it goes. All right.
Number 3.
Say again. Yeah. Page 217, problem set 8.3, number 3. Then they give you the velocity, v, is equal to 9.60 meters per second squared. No, per second. Acceleration would be, ooh, wrong thing. Meters per second. Okay? And then they ask for E sub k. What does that stand for? Kinetic energy. And what's the formula for kinetic energy? M times V squared. MV squared. Most of the time, if you see a coefficient with a 2 in the denominator, figure on seeing the main variable with a 2 in the exponent. That's a pretty good rule of thumb. Won't happen all the time, but it'll happen most of the time. So now it's just basically plug and chug. So we'll do 1/2. The mass was 4.70 kilograms, and your velocity was 9.60 meters per second, but you're going to square that. Okay? Now, we can just hang off the 1/2 for a bit. Let's first, well, whatever order you want to. In fact, if you want to do it, you could write the 1/2 as 0.5. So if you got your calculator, 0.5 times 2.7 times 9.6 squared. Then hit your equal C key. Okay. And this is chapter 8. All right. 8.2, number 15. What do you get? Whoa. No, number 3, yeah. That's the wrong 8.3. Now I'll get on the right one. Wow. Nope. Looking at the wrong one. 3. Okay. Seems a bit high, but I think it's all right. Okay, wait just a second. What do you say?
126.576.
217, is that what you said?
216.
216.5, is that what you said?
I got 0.576 unless I'm getting something wrong.
Oh, I had just two digits.
Okay, okay. Say again whatever answer you got.
216.576.
Okay, and okay. Now let's think a minute. 3 significant digits, 3 significant digits, so let's find 3. 1, 2, 3. Look to the right, that's 5 or more, so let's round this to 217. Okay, now what units? Here's a kilogram. Joules, exactly. Kilogram, meter square per second square, because you square the units as well as squaring the number. We squared the number, square the units, and that gives you joules. 217. Now, I think that's what they got in the back, too. Okay, good deal. Okay. That answer what you needed?
Yeah, without one in here.
Okay.
I just got one more.
And what is that?
8.2 page.
Oh, going back.
212.
8.2. 213. Got it. Which one?
22.
26?
22.
22. Okay. Now, this won't have the answer in the back because they only have odds back there, but we can still do it. A pump is capable of developing 4.00 kilowatts of power. 4.00 kilowatts. And they tell you that's power, so we'll use the capital P for that. How many liters of water per minute can be lifted a distance of 35 meters? So we're looking for how many liters of water per minute can be lifted, and the height here, I think that's what they call it, whatever they call it, a distance of 35.0 meters. So are they using H or D, or what are they using here? S, I think they use, okay? S equals 35.0 meters. Okay. Now, in order to do this, okay, and by the way, they give us this, that 1 liter of water, that's not a 0, that's a O, 1 liter of water has a mass of 1 kilogram. Okay. So, if you have, okay, so that's what we're looking for. Now, what we need to do is start by, you see, you got a height here, you're looking for, they say liters per minute, we're actually going to do kilograms per minute, and that's going to be the same as liters per minute, because 1 kilogram is 1 liter. Mass of 1 kilogram is a volume or capacity of 1 liter. So I think to help our thinking process, we need to break down what is a kilowatt. What is that anyway? What does kilo stand for? 1,000. So this is going to be 4,000 watts. Okay? Now what's a watt? Okay. What is that measuring? What does a watt measure?
Speed.
No?
Speed.
No, it's power. We know it's power. What is power? What is a watt? So important to keep these units in mind. No? A watt is a joule, well, joule per second. That's what a watt is. Okay? Now, what is a joule? What is a joule? And you know, it doesn't hurt to keep a little sheet near you and write down all these relationships.
Well, I think Joule was what, the word for
Yeah, joule is a measure of work, so that would be 4,000, and work is Newton meters per second. Okay? Because you got your per seconds in there. A joule is a Newton meter. Well, what's a Newton? Let's see. Yeah. A Newton is this is 4,000 kilogram meter per second squared. That's a Newton times a meter. That'll make a joule divided by second.
Right. I can't even see that over there to catch up. Back and everything.
Okay. A Newton is a kilogram meter per second squared. Think of this. Newton is a measure of force. Force is mass times velocity. Kilogram is your mass. Mass times acceleration. And meters per second squared is your acceleration. Okay. Now, we've got all our units to the basic units there now. And I'll clean that up just a little. 4,000 kilogram meter squared per second squared per second. Okay. Now,
Goodness gracious.
there's several ways you can approach this. Okay. What we're looking for is kilograms per minute. So what we either have to do is get this 4,000 blah, blah, blah per second into minutes, which probably is the best way to go. So let's do that for a moment here. 4,000 kilogram meter squared per second squared per second. Multiply this by, there's our conversion factor, and we're trying to get to kilogram meter squared per second squared per minute. We want the seconds to go to minutes because that's what we're asked for here. Okay? Now, here's the question. If seconds is down here, always put the units in their place. This line's for, the first line's there for the number, numerical values, that's for the units. Always put the units in their place.
Running out of space.
Okay? Now, which unit are you going to want where? You're multiplying here, equaling there. What unit are you going to want here? Only looking at meters, minutes and seconds. One goes on top line, one goes on below the line.
Minutes on the top, seconds on the bottom.
Now, if you did that, notice here, you'd wind up with minutes up here, and you don't want it there. You want it down there. And down here, you'd have seconds squared. You don't want them there. So let's do it the other way. Okay? And put seconds on top and minutes on the bottom. Okay? Seconds on top, minutes on the bottom. And now that looks better because the seconds are going to cancel out, and the minute is going to be a per minute just where you want it over here. Right? Okay. Now, really before I cancel that out, I should have thought how many seconds in a minute or how many minutes in a second? 60 seconds in 1 minute. So that means we're going to have to multiply that 4,000 by 60, which will give us 24 or 240,000. Is that right? That's too many, isn't it? No, I believe that's right. Yeah. 10 times that would be 40,000. Yeah, 240,000 kilogram meter squared per second squared per minute. Wait, it's coming back. Okay.
Which numbers did you multiply? I'm sorry.
I multiply 4,000 by 60.
By the 60, okay.
Yeah. See, that's why I set it up this way. If they're above the thing, you multiply. If they're below the line, you divide by them. This one's above. So, that's our setup here. Now, we got to figure out what to do. This gives us power. Okay? And this is power. It's not our normal units. It's not kilowatts, but it gives what we need. What we're looking for is kilograms per minute, right? We're looking for liters per minute. 1 liter is 1 kilogram. So kilograms per minute is going to give us our answer. What's that multiplied by? And that's a 2, by the way. That's multiplied by the work done. Well, not work done. Close to it. So that's going to give us our answer, okay? We're not quite ready for that yet, so I just wanted to point out that will be what we're trying to get to. Okay, now, this is a power unit, and power is, like we said, work per time, right? Okay, that's exactly what this is. So what we need to figure out is how much work it was to do this, okay? How much work can this thing do, okay? Well, the work is force times the distance, okay? Now the force here is our weight, okay? And this can lift, let's see.
It's about 2 pages full of work.
All right. Okay. All right. Per time. And now don't worry about these things yet. This is kilogram meter squared. Okay. I've already used the units. Let me not use units again. Let me use our parameters. Force is mass times acceleration. Now, what acceleration are we talking about here? You're lifting this thing. What are you lifting it against? If you're lifting things, this water, against what's pulling it down? Gravity. So the acceleration here is the acceleration due to gravity. So this would be, there's your mass times acceleration. Multiply that by the distance. Divide that by your time. Well, guess what? G times D, gravity times distance, if that gives you, if you divide that out, you're going to get mass per time. That's what we're looking for, kilograms per minute. So basically we take this number, divide by the acceleration due to gravity, okay, and then we'll also divide by the distance. Acceleration due to gravity is what? In the SI units? 9.80. What units? Meters per second squared. Perfect. So, if we take this number and divide it by the G, 9.80 meters per second squared, also divide it by the distance you've listed, that's your S. I probably should have put S here rather than D. That's 35.0 meters. Look at what happens. Meters per second squared, that takes one of the meters per second squared, divided by meters, it takes the other one. Sure enough, you're left with kilograms per minute, which is the same as liters per minute. So this will do it for you.
That's the answer?
Yeah, but you got to do the math.
Oh my goodness, 9.8
Okay.
times the
24,000, I mean 240,000 divided by 9.8 divided by 35. That will do it for you.
Let's see what this comes out to be.
Your units are your friends. Let them help you figure out how to deal with this problem. Did you also divide by 9.8? Did you divide by 9.8 as well?
I think I did.
Oh, okay, that's fine.
I believe it. Let me go back.
240,000 divided by 9.8 and divide that by 35. What do you get?
699 point.
A little louder.
699
699.708.
.708.
It sounds like it's going around pretty close to 700. And what units will that be? It should be liters per minute. Okay? Let's see if that's what they got in the back.
Oh, you said it's not going to be in the back because you said it's...
Oh, that's right. I'm pretty convinced that's your answer. 700 liters per minute.
That's a pretty long problem.
Yeah, it is, but I mean, I sort of stretched it out there trying to recall all those, help you recall all the formulas and relationships between these things, so you hopefully see how to do it. All right. Any other questions? All right. Then today, there's no other question. You still need that a little longer? Everybody got it? Okay. Then today we're going to be doing example 4, bottom of page 322, I believe it is. Chapter 12, matter, and 12.2 is what we're in now, and that title is, if I can find it, this is a long section, properties of solids. Okay? So number 4 is a support column is compressed a very small amount. So basically you've got this column here. Okay? You got things resting on the column. Big old building, bridge, something here is on this column. Okay? Resting on top of it. Okay? And support column is compressed 3.46 times 10 to the minus 3 meters. So this is going to be compressed a very small amount, and this amount is about, what's that? Page 322, example 4. The basic formula we're using here is S is equal to F over A. I think that is. No. No, that's the stress. Ah, there it is. It's F over delta L is equal to K. F over delta L is equal to K. To me, it's so much easier to remember it this way. F is equal to K times delta L. That's so much easier to remember than the division. They're the same formulas, it's just written different ways. Okay? Now, the delta L is how much it's compressed. That's your delta L, and that was 3.46 times 10 to the negative 4 meters. And that would be 3.46, 0.346 millimeters. Now, a millimeter is the thickness of a dime, and this is a third of that. Okay, it's a pretty small amount. Okay? Under a weight, the weight up here, which will be your force, this is 6.42, and this, by the way, is your delta L. Your weight up there is 6.42 times 10 to the 5th, if I'm reading it right, newtons. That's a lot of force. You're compressing this huge column by a small amount. It says how much is a column compressed under a weight of 5.80 times 10 to the 6th newtons. So this is your setup. That tells you how much it was there. We're not looking for anything there. The second part says, what is your delta L2? This will be delta L1. Delta L2, if F2, here's your F1, if your second force is only 5.80 times 10 to the, oh, I'm sorry, it's a bigger one, 10 to the 6 newtons. This time you're going to put almost 9 to 10 times as much weight on it, so you expect to compress it a little bit more. Not a lot more, but a little bit more. Okay? How would you proceed with this one? Basically, this first bit of information they give you here will enable you to calculate your K. right? Okay. Once you've calculated the K, then you can rearrange this formula like dividing by K, and that will give you your new delta L. This will be delta L2. This will be delta L1 and force 1. This will be delta L2 and force 2. So that would be force 2 divided by your K. The same K that you got before. So you see the process here? The first set that they gave you enables you to calculate what is your compression constant, the Hooke's law constant. And then the second uses that constant to come up with the new delta L. Okay? So, using what they gave us here, this is going to be an enormous number, so don't be surprised. 6.42 times 10 to the 5th, that will be newtons, divided by 3.46 times 10 to the minus 4 meters. That will give you an answer, K, in newtons per meter. I don't have enough room over there, so I'm going to write it here. So it's going to be a pretty large number, something like 10 to the 9th. About 2 point something times 10 to the 9th. What you get? Okay, remember how to do your scientific notation? 6 point,
Was it EE?
yeah, the EE key. It's 6.42 EE. Don't do it times 10, just do EE or EXP, depending on your calculator, 5. That gives you that number, 6.42 times 10 to the 5th. 6.42 EE or EXP 5 divided by 3.46, I think that is. I can't read my writing. EE or EXP negative 4. Then press equal and see what you get. It's 3.46. EE or EXP negative 4. No, it's going to be 1.9 something. I'm sorry, I said 2 point something. I was misreading my writing there. Two 2.9 something another times 10 to the 9th. I'm guessing. Anyone get an answer yet? Okay, on your, I have to look at your calculator because different calculators do different ways. Goodness, I'm still. Okay.
I don't know, we have to go all the way back. Put the numbers in the beginning.
Yeah.
Yes, I did 6.42 the E, and then
Yeah, 3.46, and then you do the EE again, that second EE, you did that, and now you do, see this negation
oh,
key?
down there.
Minus 4. Okay, then you press equal.
That's
Whoa,
not
that's a
right, is
huge
it?
number. But you see, if you count your decimals, 1, 2, 3, 4, 5, 6, 7, 8, 9.
But I'm saying, is that right?
Yes, it is. I said it 1 point. I said 1.9. It's 1.8 something.
How did they get it in the book, though? That's what I'm trying to
Okay, wait. We're not through. Okay. Now that, your calculator gave it just a thing. Let's write it in scientific notation. That's 1.8. What was the next digit? Did y'all get this too?
1855.
Okay, let's go at 1.86 times 10. And how many decimal places did you have to move it? I believe it was 9, wasn't it?
Yeah.
Times 10 to the 9. And that would be newtons per meter. Those are your units, newtons per meter. Okay, we take that number and do our new delta L, delta L2, that's what we're looking for, is equal to F2, which is 5 point, I believe that's 80, isn't it? 80 times 10 to the 6th newtons. Divide that by the one we just got, 1.86, times 10 to the 9th Newton per meter. Okay? Now here your newtons are going to cancel out, and you're going to be left with meters, which is what you want. That's your delta L. And it's going to be a pretty small number, something 10 to the minus 3. The other one was 10 to the minus 4. This will be 10 to the minus 3. I'm guessing it's going to be 2 point something times 10 to the minus 3. Something in that ballpark. .8 times 10 to the 6th, EE6 divided by 1.86, EE9. Anyone got it yet? These calculators sure are slow, aren't they? Okay, no, I'm just kidding.
I said it's the 3.118.
3.118. Let's round that to 3.12 times 10 to the minus 3. Is that what you get?
Why do they have 10 to the 7? Oh.
What's that?
They got 10 times 10 is 17 on here.
Okay.
From what I'm looking at the calculator, I don't know.
Okay. I sort of have a feeling.
Gotta put something in wrong. You see?
Whoa. I think. Okay. Let's go back up to your thing. How do you get there? Just go up here. Okay. 5.8 times 10 to the 6th divided by 1.86 times. Oops. There you did it times 10. Don't need the times 10 in there.
Oh,
Okay.
take it out.
Remember,
Well, why do you do it in the first one?
we didn't. I hope you didn't.
Yeah,
You just
so,
eat.
yeah.
Oh, you did, didn't
Yeah.
you? Yeah, you don't do it there either.
So you just leave the 10 out?
Yeah, it's EE and then press the digit. So, clear. Oh, it cleared it all.
That's
Okay,
fine.
okay.
I can rewrite
You
it.
do EE second EE. Oh, okay, only once. Okay,
Go back.
Yeah. 5.8, the second EE, just press that once, okay? And then do 6, that's 10 to the 6th,
6.
divided by 1.86,
Okay.
and then do your EE key, second EE. No, the second EE.
Ah! Second E, that's one time.
Right, one time. 9.
9.
Equal. Yeah, that's 3.12 times 10 to the minus 3. That answer is perfectly fine.
Okay.
Okay? Now,
Oh, wow.
and that's meters, okay? Because your newtons cancel out, that left you meters. Now you could rearrange that and call that 3.12 millimeters, because 10 to the minus 3 meters is a millimeter. Milli is 10 to the minus 3 thousandths. And that's what they have in the book too. Now, that would be like 3 dimes and a sliver of another dime. That's how far you've compressed it this time. With a million, let's see, almost 6 million newtons of force on top of it.
Okay, let me write this down without this calculator crap.
Okay.
So you don't have to press the E one time, right?
Yeah, it's second EE. The EE is
What
what's
is it?
above there, so you don't do it twice. You just second EE. Second EE is just one press.
What's the 2 of them for?
Well, it's exponential. It's what that stands for. And on yours it's a EE, so you only press it once to get that EE.
Oh, okay.
Yeah. Now, there's a physics connection here, talking about engineers choosing materials based on two factors, cost and strength. They give a pretty good rendition here. They say in the late 19th century, American engineer James Eaves constructed the first steel arch bridge over the Mississippi River. The steel used was not much stronger under compression than iron, but was more than twice as strong as iron under tension, blah, blah, blah. So I think they give a picture, and that's on our next. Does anyone need this any longer? Okay. What's that? I'm sorry?
I wrote the final answer. I'm having to go back and figure it out.
Okay, well, it's one formula, you use it twice. The first time you use it with what they gave you to calculate the K, then use the same formula again to calculate delta L. So, yeah. Okay. All right. Let me get out of here and go back to the other. And this is actually, I think, if I'm not mistaken, oh, no, this is not Eads, this is Darby's. So if you read back, I'm sorry, if you go back up one paragraph, what we're doing before, they were talking about the ancients used stones during the 18th and 19th centuries. The English engineer Abraham Darby built the first cast iron arch bridge. The low-cost high compression made it a much better alternative than to expensive and heavy stone arch. In later years, however, the cast iron bridges problems became evident as the nature of iron under tension and shear stress is called fractures, and they also rust like crazy. So this was actually Darby's cast iron bridge, constructed in Coalbrookdale, England, 1779, and this is still standing. So they have some problems, but they do pretty well. All right, that does finish section 12.2. Homework exercises here, any of the odd number exercises 1 through 19. There's a whole bunch of them. Do some of each basic type. Okay? So let's move on to, oh, wait. This is another thing they're mentioning here. This is what they call pre-stress concrete. It requires tension in the cable while the concrete dries. After the concrete dries, then the tension's released, and that puts the concrete under tension, under compression, and that makes for a stronger bridge. So that's what they use nowadays in these bridges. Were any of you watching the construction of Malfunction Junction as they were building those supports and things there? I never saw that they did pre-stressing, but I wasn't there during the day. There was usually nobody working when I went by, but I bet you they pre-stressed because they had all sorts of things sticking out of it, and I bet you that's from pre-stressing the concrete. It's supposed to last much longer. You can read that parts in the book. You're not going to be tested on it. All right, now we get to liquids, okay? And some of the terms we talked about before, we're now going to bring up again. Where is my, there we go. Go back to current slide. And I'll also have to get my color back. Okay. As noted previously, a liquid is a substance that has a definite volume, but it takes the shape of its container. What that means is the molecules stick together pretty closely, but they're not in a rigid structure, so they take the shape of anything they're in. Now, part of the reason for that, and I think we mentioned these terms before, is the cohesion and adhesion. Does anyone remember these? Okay. Cohesion is force of attraction. between like molecules and adhesion is the attraction between unlike molecules. Basic difference there. Now, the first, they give this example. Have you ever tried to pour molasses, especially if it was cold? It takes a long time because the molasses sticks together, that's cohesing between each other, and it takes a while to get it to pour. Now, you stick your finger in it, it comes out on your finger, that's adhesion, unlike molecules. Sticking together is like molecules, that's cohesion, and adhesion is unlike. So molasses do both, okay? Water does both, okay? You can just think of this. You can put a very heavy boat in water and it will sink down so far, but the water molecules just won't spread out of the way. They're hanging on to each other, and after a while, if the boat's big enough, it will float, okay? But put a plate in water or glass, but lift it up, water sticks to the plate, okay? Well, cohesion is the water molecules hanging together. If you've ever done a belly flop in a swimming pool, you know the water molecules hold together really well, okay, because that hurts, okay? You're picturing that of me, aren't you, okay? I can tell, okay? Now, but when you come up out of the water, you're wet because it's adhering to you. So that's cohesion, adhesion, okay? Now, we're going to see some of that in a later slide. Let's move on. What I've been talking about, that cohesion, one way that expresses itself in water and other liquids too, is what we call surface tension. And that's what gives you this raw stomach when you do a belly flop. There's a picture in your book that really is, it's real. Nobody's done anything to it. And if you do it carefully, you can do this. Have a cup of water and take a needle and just very gently lay it down flat on the water top, not disturbing the water, just lay it down very gently. It'll float. That's made out of steel, and yet it's floating on water. That's because the water molecules cohere together so tightly they don't want it to break through. Okay. Now, why do you wash your hands or wash your clothes? What? To clean them. Okay, do you just use water? Why not? It doesn't clean as well. It will get some of the stuff off, but not total. Because water tends to hang together really tightly. It doesn't want to fight the dirt and grease or other things. But what else do you use? A detergent, a soap. And you know all that's doing? It's not really cleaning your clothes. It's making, this sounds so bizarre, the water wetter, okay? Because what it's doing is breaking that surface tension of the water, and now the water contacts it a lot better, okay? So if you had that same needle on a floating in the water, take a drop of detergent, Dawn or liquid detergent or hand soap, a drop of that, and put it in there, you'll immediately the needle fall, because the water molecules don't hang together as tightly anymore, so they don't hold the needle up anymore. It makes it makes water wetter. It makes the molecules get closer to the dirt and separate them. See, before the water molecules were hanging real close to each other. So actually, and by the way, soap, detergent, those are all called surfactants. Surfactants from surface tension. It breaks the surface tension. That's what the surfactant does. Okay. Now, Mercury has even greater surface tension than water. I don't know if you've ever seen anyone spill or put mercury on a surface. It forms these little balls. Now, they're not solid. They look like they're solid, but you can touch them and they're liquid. But they make tight little balls because it doesn't want to touch anything on the surface, so it's only cohering to each other. They show it here as being a little flatter than that. And they also show a drop of water or any liquid out in space forms a perfect little sphere because there's cohesion. The molecules are hanging together. The smallest surface for a volume is a sphere. Okay? Now, under gravity, this is where you get the teardrop shape. You know, most of it's here, but it gets a little narrower at the top because gravity's pulling it downward. That's all in your book, and that's what they're talking about. All right. The next term they talk about here is as a characteristic of water and of liquids, and this is viscosity. Has anyone ever heard of viscosity before? Or the verb form would, no, noun form, no, the adjective would be viscous, a viscous fluid. What is viscosity? Anyone know? Okay. Here's the definition. Internal friction. Okay, I wouldn't have ever thought. Yeah, well, that's right. Internal friction okay, of a fluid, okay, caused by molecular attraction. Again, cohesion. Okay. The place where you'll see this most likely is on your oils. Anyone put oil, change the oil in your car, that kind of stuff? If you notice, yeah. If you notice on that, most of the oils have some number on top. Very simple oils would be SAE 30, SAE 40, SAE 15 or 20. Most of them, though, modern ones today, will be something like 10W40, 10W30. That's a blend of oil, so you get a wider range. Okay? That is a measure of viscosity. Now, here's why you need the blend. If you've got an oil that works great in the wintertime, where it's really cold, the engine oil is at the cold temperature, you need a less viscous oil so you can coat all the surfaces. Okay? So you need one that won't stick together so tightly. You want a thinner oil. But if you use that thinner oil in the summertime, when the temperatures are really hot and your engine gets really hot, then the oil is too thin and it won't give the lubrication you need. So that's why they do a blend, 10W40, 10W30, to give you oils that'll work winter and summer. Now, when you live somewhere up north, way up north, like Minnesota and those places, you have to change your oil with the season because you just can't get a good enough blend. So you have to use a very low viscosity oil in the wintertime and a pretty high one in the summer, because in Minnesota, you still get in the 90s in the summer, but you get in the minus 30s in the winter. So you have to be pretty careful on that. So that's viscosity. Okay? And they show the picture in the book. Cold oil is more viscous than hot oil. It sticks together. There's more internal friction. Okay. And that leads to, or doesn't lead to, but it brings up another area called capillary action. Now, this may be something that you actually wind up measuring some if you're doing sonography. Okay? If there is I'll get to that in a minute. So let's see what capillary action is. Behavior of liquids. We all talk about liquids here. Behavior, I think that's how you spell it, of liquids. Okay? That causes the liquid level in a small diameter tube to be different from the large diameter tube. this is a pretty vague description. Behavioral liquid that causes the liquid level to be different in small diameter, is that what they call it? Small diameter tubes. From that's large diameter tubes. Okay. Now, you may have seen this before. Well, I think this one we do have a slide. So let me get out of this. Everybody got this that needs it? Okay. And let's go to this one. All right. I don't know if I'll need the other. Okay. This is probably somewhat of an exaggeration, but not too much of one. If you put a large diameter tube, middle diameter tube, and a very small diameter tube into water, water will actually climb the tubes a little bit, no matter how big. More, it will climb some in a large diameter tube, more in a medium, and even more. Now again, this is a little exaggerated, I think, but yeah, they're trying to make a point here. And here's why. Because water, even though water has a pretty low viscosity, so it doesn't resist movement too badly, but it also hangs together well, but it also likes to attach to surfaces. So what it'll do, the water in the tube, you see, even on the outside of the tube and on the inside of the container, you can see it climb the container just a little bit, climb the tube, because the water molecules are attracted adhesion up the tube. Now, if this was a wax tube, it would go the other way, but most glass, it adheres to it pretty well. So it will climb the tube. Well, it climbs the tube inside a small tube, and because then cohesion, it pulls the other water molecules up. So it actually moves up the tube. Okay? And in a medium tube, it will move up further because there's more surface area for it to be pulled up and less weight that it has to lift. Okay? And in a really small tube, it really pulls it up. Okay? Now, where have you seen or heard the term capillary before? Where?
Lab.
What are they talking about?
Blood.
Blood vessels.
I was
Okay?
thinking about blood because they use those little tubes. You know, and they normally
Yes.
just run up.
Exactly. If you do a stick and hold that little capillary tube, the blood just goes right up the tube,
Yeah.
just like this. And that way you don't have to suck it up. And then, ooh, you don't want to do that. Huh?
Vacutainer. That's what they call them. Vacutainer.
Okay. Now, do you have you don't even have a rubber thing on it. It just pulls it up itself, doesn't it?
No, it has a rubber on it.
Oh, it does.
Yeah.
Yeah. But if you've ever seen one, they do have them that are really small tubes that you just touch the edge of the blood and it just goes up. Yeah.
Oh, you some of the little sticks?
Yes,
Oh,
really
you talking about the
skinny
little
ones.
sticks.
See,
Yeah.
that's the small capillary
They
tube.
call them little pipettes.
Yeah, pipettes, exactly. Exactly. Okay? And that's why water climbs, the blood goes into those because it's attracted to the material in the thing and it pulls it right in there.
Yeah.
That's capillary action. The reason it goes in a small tube more than big. So in blood, what do we talk about with capillaries? What are the capillaries? Very tiny little blood vessels. You can see blood vessels here, and it's hard to see the arteries because they're deeper. But if you could see them, then you'd see them too. But the capillaries are the very tiny little ones. That's where the action's going on.
They call them Spider-Man.
Spider. Okay. Yeah. Okay.
You know some.
Yeah. Fortunately, I don't have any yet, but my mom had some. And But the thing is, even, I'm talking about ones that are the size of hairs. That's where, when I move my muscles and stuff like this, they're the ones that are exchanging the oxygen to give the energy to happen. That doesn't go on with these. These are just highways. These are just carrying the blood. The capillaries are where it actually is going on.
They can do a procedure to make them, like, not really show. I seen it on TV. On Dr. Pimple Popper.
Yeah.
And the lady came in and she was like, she had a whole bunch of them in the back of her legs.
Oh, you've heard
the
the spider veins, yeah.
Yeah, and she said she wants to get rid of them.
Yeah. Yeah. I don't know what that's doing. I know there are procedures that, see, basically what's causing those, something's getting blocked, and then the blood is getting visible, okay? And they'll go in and strip them. It sounds horrid, but my mother-in-law has had that done more than once, I think. So that's what's happening with them. And water in general is going to come up. And what's left at the bottom, this is called a meniscus, okay? Now, if you've ever taken a thermometer, the old mercury thermometers, taking temperature with that, you know the meniscus goes the other way in that. And that's because mercury doesn't like to climb the tube. It tries to stay away from it. Just like the drop of mercury on the table, it'll try to stay away. So its meniscus is on top, where water or alcohol, its meniscus is on the bottom. Okay? Mercury surface is convex, and water surface is concave. Just slope down. In mercury, you stick these things in, and this will push it down. That pushes it more. This pushes more because it doesn't like to touch the sides of that tube. It has to touch some, but they go in exactly the opposite directions that water or alcohol will go in these. Okay. So that's capillary action. All right. Now, so spider veins, those are big capillaries, but they're so there was a French anatomist, I think he was, named PHY112, and he talked about the flow through capillaries. And that's what I was saying. Maybe y'all will be in sonography actually seeing places that blood is collected that it shouldn't be collecting, or aggregating, and possibly where capillary tubes have burst or things like this. And that's what happens a lot in, I'm trying to think. I believe when you have a stroke or something like that, you've had some blockage, and if there gets to, or breakage, and then blood leaks out into an area where it shouldn't be. And that may be some of the stuff we all are looking for when you're doing sonography. The only sonogram I had a young doctor, which sometimes is not a good thing, and he seemed to be worried about everything. And he was so super cautious on everything. And I also think he thought his job was to perform more procedures. And I don't know if he thought he was getting paid for more procedures or what, but he wound up, he microturia or urea or something like that. Very trace amount, microscopic amounts of blood in my urine. So he was convinced I had bladder cancer. Okay. Like my mom was, if you had a symptom, she could find the most deadly disease to match it. She was a nurse. And so that was her specialty, was find the most deadly disease that fits your symptoms, and then to not panic, but get you to the doctor.
I did diagnose myself one time, and when I went to the doctor, that was exactly what they said that was going on.
Right. You knew too much. And, like they say, the doctor who treats himself has a fool for a patient, so never mind. That's, don't do that, go see, because you're biased. Okay. But anyway, that's capillary motion, capillary action, they call it. Okay. These are the pictures you see on this page. There's another set at the top, which is pretty interesting. It's a combination of the adhesion and cohesion. I think that's all. I mean, they just go on and on about it. Okay. And I've already mentioned the meniscus. That's the level that you see there. Experimentally, scientists have found that liquids rise in capillary tubes. They tend to wet and are depressed, and they tend not to wet. Elevation and depression in the tube is inversely proportional to the diameter of the tube, which we've seen here, and the elevation and depression decreases as temperature increases. As you heat that stuff up, then those will come down, these will go up, because the surface tension, the cohesion is lessened when you heat it up. The molecules move faster, just like viscosity is lessened when you heat it up. Okay. I think we're ready, and here's oil viscosity. You see the gal changing the oil in her car. Okay, good deal. Now, the next one, 12.4, is properties of gases. So let's go back to our other slide so I can write down a few of these things. And I have to get my color back. Okay. Remember, we said gases tend to fill a container. Hey, it doesn't matter what shape or size, gases are going to fill it up, because gases just move around wherever they want to. Now, if you have a confined gas, though, in a container, now let's think balloon, basketball, volleyball, something like that, and you heat it up, you're going to expand that. You cool it down, it contracts. Blow up a balloon sometime, get it nice and full, put it into the freezer. For not very long, it'll come out limp. Leave it out for very long, the likelihood it'll maybe not get back to its original, but it'll start expanding again. This happened to me. I was working with a kid. He and his mom and sister went to our church. This is up in Lincoln, Nebraska, and her mom and dad were divorced. The mom and dad were divorced, and the dad moved out of town, and so she was left raising, and she was doing fine with Lindsay, but Matt could be a sort of a problem, okay? So she was begging guys from the church to sort of work with him some so he could have some male exposure. And I thought, I don't have kids, but he came out and played. He was a really good athlete, and he was still in high school. Came out and played with the church softball team, and he was really, really good. So I encouraged him, and because he was a little hesitant with all these old guys, so we hit it off pretty well. So I started doing things with him. Went over one cold, this is Nebraska, cold Saturday afternoon, Sunday afternoon, just was really cold. And he had left the basketball out rather than taking it in the house. He said, "Oh, I must have got a leak in my basketball. I better go pump it up." I said, "No, wait a minute. Just take it in the house, let it sit there for a while, and then we'll play later." He said, "I need to pump it." I said, "Just do it." So he took it in the house. It warmed up to room temperature, went in. It was just as tight as it could be, because gases contract when they cool, expand when they heat. Solids and liquids do too, but just a tiny little bit. Gases do it big time. So that's what we're talking about. Expansion is a property of gas, is a rapid movement of its molecules causes the gas to completely fill the container. Now they're just talking about filling a container. That's expansion. Okay? And diffusion is the other side of that. Diffusion, that's the properties of a gas to get as far apart from its other gas molecules as it can. Okay? Process by which the molecules of gas mix with molecules of solid, liquid, or another gas. And you know this. This is the thing of opening the bottle of ammonia, and soon the whole room smells of ammonia. You would get it first, but you would get it later. Whole room. That's diffusion. Now, this isn't a gas, but it's my way of thinking of diffusion. I like to garden, either vegetables or flowers, that kind of stuff. I just like messing in the yard. And my theory on this is if you watch Bermuda grass, it practices diffusion. It goes from areas of high concentration to areas of low concentration. If you got it in your yard, you clear it out of your flower bed, it's going to head to the flower bed or to the garden because it's going from high concentration to low concentration. That's the principle of diffusion.
Is it a good grass, though?
What's that?
Is that a good grass?
It depends. Not in your flower bed, but it's good grass to have in your yard. Now, another definition here, fluid. If I say fluid, what do you think? Okay, we all think liquids. But a fluid is a substance that takes the shape of the container that can be either a liquid or a gas. Oh, any liquid is a fluid, but so is gas. It takes the shape of the container. So fluid is not just liquid. When you're talking about fluid flow, that works for the air coming out of the vent system, just like it does water coming out of a pipe. Same principles apply. So a fluid is any liquid or gas, okay? Any substance that takes the shape of a container. That was all that 2.4 has. Those three words, there's a little bit of verbiage in between, but I'll let you read that if you've got your books. So let's move now to density. Density is a property of all matter, not just solids, not just liquids, not just gas, any matter. It's a property of all three states of matter, and there's two types. There's mass density, that's an S there. Mass density is mass per unit volume. Now, capital V is volume, little v is velocity. This is volume. And then you have weight density, and that is weight per unit volume. Okay? Now, why do you think we would have two types of density like this? Let's think back to that concept of mass. In the U.S. customary system that we usually use, what's the unit for mass? We never use mass. When you do use it, it's the slug. No one uses slugs. We always use weight. So we use pounds per cubic feet, pounds per milliliter, something like ounces per milliliter. Weight measurements. It's only in the SI system that you generally use mass density, okay? Because here on the surface of the earth, mass and weight are equivalent, pretty much. If you go up into outer space, they're not anymore, but here on the surface of the earth. So the way they describe this is mass density, they use the symbol D sub M, and weight density, they use D sub W, okay? And rather than weight, what they use for weight is, and this is actually a pretty good term, you just don't see people use it that much, they use the symbol F sub W. Yeah. The weight density is the force due to weight. And what's that associated with? Gravity, the acceleration due to gravity. So those are our two formulas. They're completely different units. Kilogram per cubic meter or pounds per cubic foot. Okay, you'll use both of those. Okay. Now, they have a little note here. Conversion factors must often be used to obtain the desired units. Now, most of the time, we've been using conversion factors when I do that little train track type thing, what goes on top, what on bottom. This section, you're probably going to use this more than normal. And let me refer you to the back of the book. Okay, have I told you this one before? No. Okay, if you turn to the back of the book on page 686, that's your Appendix C. These are tables. Now, the table 1 is U.S. weights and measure. That's just has a lot of those conversions in it. Conversion table for length. Beginning with table 2, conversion table for length. Table 3, conversion table for area. 4, conversion table for volume. 5, conversion table for mass. 6, conversion table for density. 7, conversion table for time. 8, conversion table for speed. 9, conversion table for force. 10, conversion table for power. 11, conversion table for pressure. What's that? I can't hear. I'm sorry.
British thermal unit.
Oh, BTUs, British thermal units. That's a unit of energy, specifically heat energy. Like calorie is in the it's the metric system. BTU is in the U.S. customary. British thermal unit, because they used to use the British system. Then there's a mass and weight density table, table 12. That will be one you might find quite useful in this chapter. The top part is mass density. No, one column is mass density, the other column is weight density. Mass density in kilograms per cubic meter, which are huge numbers. I don't like to use those, but the book, that's what they like to use. I like to use grams per cubic centimeter. Those are much more usable numbers. Weight density is pounds per cubic feet. They usually are pretty reasonable. Okay? And they give those for solids and liquids in the top part of the table, gases in the bottom part. And that, table 14, conversion table for heat, work, and energy. Those are most of those conversion tables. So if you don't know or remember them, you can always go back here and use these tables. I have a page that I mark them so that, because I don't know what y'all do, but it's not just this class. Every class I'll have people go along doing, and then suddenly they give me the answer in newtons, but the key is in pounds. So I have to then go and make my conversions to see if you got the right answer. I'm not requiring you to do one particular thing, but I don't want to mark a right answer wrong or a wrong answer right. So I have to go back to the tables and calculate, because I don't memorize those things. They're not worth it. I'll look them up when I need to use them. Okay. So here is density. Okay. Now this is going to be pretty small type here. It's a lot like that table I looked at in the back. And frankly, mine looks really fuzzy. It's better on the board. This is really poor on my screen. It's better on the board. Most of the time it's better on the screen, not as good on the board. It's still a little fuzzy. Here are some of the common densities of fairly common substances. Aluminum. Now, I don't like kilograms per cubic meter, because a cubic meter is a huge amount of volume. Okay? Remember this illustration I gave you before? A meter is approximately the height of a doorknob. Approximately. And that's about the same as the width of a door. This door, anyway. And if you came out something about that same thing, that would be a cubic meter. From the doorknob, door handle there, across the door, out to where I am. Just think if that was that much of anything. Water, you can lift it. Okay? Anything. That's a huge amount. And that's why the numbers are so big. The thousands, 11,000, 13,000, they're just way, way too big of numbers. If you did gram per cubic centimeter is about like your little fingernail. It's that tiny little sugar cubes you see sometimes that don't sweeten anything. Okay? That would be a cubic centimeter approximately. Okay? And a gram per cubic centimeter, that would be 2.7, 8.7. Much more reasonable numbers. Okay? So that's what I like to use rather than kilograms per cubic meter, but that's the SI unit. Now, the weight density, pounds per cubic feet, These are fairly reasonable numbers. They're still a bit big, but you can't do much with them. If you do pounds per cubic inch, they're too small. If you do ounces per cubic inch, that might be more reasonable, but still, you have to convert them to pounds. And English conversion or U.S. customary conversion, it's just so hard to do. Okay, but let's get a few of those. I'm going to just move the decimal 3 places, so I'll deal with that. Aluminum, 2.7 grams per cubic centimeter. Brass, 8.7, much denser than aluminum. Concrete, about 2.3. That would be the concrete blocks there. Okay. Copper, 8.89, almost 8.9. So a little bit more than brass, but not a lot more. Well, one of the components of brass is copper, so not surprising they're pretty close. Quartz, very light. That floats on anything. That's about 0.24. Okay. Ice, 0.97, right around 0.9. Okay, remember that. We'll come back to it. Iron, about 7.8. Lead, 11.3.
No wonder it killed people.
What's that?
No wonder they was taking it like the lead. Is that the same as like paint? Yeah.
Okay. Yeah, but the thing with that is, if you ingest it, and kids, in playgrounds, some of them. Okay. What lead does to paint it make it adhere better, okay? That's why they started using it. They didn't realize it was also toxic, okay? Deadly, you're absolutely right. So a lot, and especially those made in China. The paints on those, on toys and stuff, we don't know whether it's lead-based or not because they don't have as stringent of environmental protection as we do here. Politicians don't act like, oh, this bad stuff that regulate, you don't want to do. Oh, yes, you do, because it makes it safer for kids. Okay, so if those toys are made in China, be wary. Okay, it may be those. The kids are going to put them in their mouths. They know the young kids especially. So that's what you have to watch out for. And they've done some tests on playgrounds, especially older playgrounds that the paints were. In fact, in the Navy, we would go to Philippines or Japan or somewhere like that and have our ships painted, okay? Because we look better and we want to look good, but it was also so much cheaper. Those poor people. I mean, they put on the paint with rags. They didn't use brushes or rollers. They did it, stuck their hand in it, and the paint they used, the base coat. Naval ships are gray, haze gray and underway. Okay, they're gray, but that's not the first coat. The coat that's right next to the metal, the steel in the ship, is a red coat, and they called it red lead because it stuck really, really well. Those people were out there painting that red lead on with rags, really. And I didn't know at the time. I don't know if it was still lead, but I'm afraid it may have been. And if I'd have known then what I know now, I would have had. It wouldn't have done any good, but I would have had to object. I was just thinking, you may be shortening these people's lives, but they didn't care. They were foreigners, I really hate that attitude. But anyway, that's and a lot of the paints in things are lead. But this is the reason. Lead is what they call a heavy metal. That's not to do with music, but it's a heavy metal, and when you ingest it, it interferes with, especially young kids, their development. Okay, mental development and other physical development as well. It can affect us older folks too, but not nearly as much as it would a young growing child. Wood, white pine, 0.42. The liquids, alcohol, 0.79, gasoline, 0.83, 6.8, I can't read. Mercury, goodness, that's a liquid. Look at that. It's denser than lead is. And mercury is also toxic to us. That's why you don't like kids playing around with things, because that is a heavy metal that is not good for development. Oil, just a little bit more, more dense than gasoline or alcohol, 0.87. Seawater, 1.025. I'm giving you in grams. Water, 1.000, okay. Pure water is, and I'm talking about grams per cubic centimeter. Here's why. The first measure they came up with in the metric system was the liter for length. Okay, that's about from this finger to this ear. That's about a meter, about the distance. Okay, well, that's a pretty long distance. Okay, relatively speaking. So they broke that into hundreds, a centimeter. That's a little bit less than an inch. A little less than half an inch, actually. That's about a centimeter. That's about an inch. So less than half of that.
So, I'm just thinking, like, isn't it like they, you know how they say, like, some radiation is not good for people? I'm like, what
kind?
is radiation?
Oh, yeah.
So what would that fall up under, like, radiation?
Okay. Radiation is a nuclear event. Okay. When you have large unstable nuclei, that's where the protons and the neutrons live, not the electrons. The protons and neutrons. If you have an unstable nucleus, then it's going to emit radiation. Now, some radiation is called alpha radiation. That's 2 protons, 2 neutrons. That's all. That has a charge to it, a +2 charge. That is problematic, but it's easy to shield. A piece of paper will keep alpha radiation from getting to you. So clothing, anything like that. A microwave, that's another form of radiation. It's all, okay. What I just said, okay.
Interesting.
Yeah. Okay. There's 2 types of radiation then, if you include things. One is electromagnetic radiation, which is not nuclear. Okay, I thought you were talking about nuclear.
Well, yeah, I'm talking about like radiation that patients get.
Yes, okay.
Yeah.
That's usually nuclear based.
Yeah.
You've got something that is, and basically what they use it for, okay. Let me back off and do electromagnetic first, okay. That's just electric and magnetic waves go together. I can't do this well. One goes up and one goes like this. I can't do it, Yeah. They're not in phase, but they go with each other, and they travel. Now, the higher the frequency, the more energy they have. Light, normal light, we all handle no problem. Okay. That's a certain spectrum. On longer wavelength, but shorter frequency, lower energy, we have infrared radiation, which is heat, okay? And then you get smaller than that, and you get down to radio waves, and I think microwaves are sometimes down there too. Usually that's not bad. Now here's why a microwave can cook food or kill germs. Because microwaves in your microwave oven are at a frequency that really resonates with water. So it makes the water molecules move very, very rapidly, and when they do, they heat up. And that's why food cooks basically from the inside out, because the water is all over inside as well as a little bit outside,
Yeah.
but it cooks from the inside out. So back when they first came out with microwaves, you would hear horror stories, whether any of them were true or not, like the little old lady that put her dog in the microwave to dry off after the bath. No, okay. I don't know if that ever happened, but that was the story, okay? Yeah. The blood would start boiling. I mean, the liquid, No, you don't want that to happen, okay? So that's why you don't want to be exposed to microwave, because you're filled with water, okay? And that's why they have, if you notice on the microwave ovens, there's that grid that's in between the
Right.
glass or the plates there. That's to keep the microwaves from coming out. So yeah, you don't want to expose yourself. That's only because the water frequency and oils also, they will resonate, and that's why they heat up and cook from the inside out.
So you want to say eating out the microwaves?
What's that?
Would you say eating out the microwave is bad or no?
No, eating it, I mean, all it's doing is heating up the food. I mean, it just does it from the inside out. But you don't want to put your hand in there. It won't even work if the door's up. That's why they made those safety things there. So you don't want anything alive. But actually, you can use microwave to disinfect something. Because germs can't live. The germs are mostly water. So actually, in soil science, and where I came from, they used to kill the microorganisms in the soil. They put it in the microwave. And it's much cheaper than heating it up, because you can change the soil structure by heating it up. So that's why microwaves are sort of bad for living things, because of that interaction with water. Now, you get higher energy rays, like ultraviolet rays, shorter wavelength, higher energy. That's what causes skin cancers, and it causes sunburn, because you're killing cells, and your body is trying to pump more melatonin, is that it, out to the surface to keep you from burning. And that's why people get tan. Oh, I want to get tan. I go lay out in the sun.
That's bad.
Yeah, it's
my
not.
skin was on fire.
Yeah.
That's horrible. Summertime and me don't get along.
And then they keep going higher and higher energy. Then you get into some of the cosmic radiation and that kind of stuff. That's really getting the bad stuff. That's getting closer to what you get with nuclear energy, because the energy coming out of nuclear reactions are much higher energy. So I started with alpha particles, and there's beta particles, which are basically, I want to say electrons, but they really aren't. They're this is a different name, I can't think of what it is, but they come from the nucleus, but they're negatively charged just like an electron. Now, those can cause some damage, but the others is gamma radiation. And you may have heard of gamma knives and gamma things like this. It's really high energy. What they're doing with that is usually using that radiation for a couple of things. One thing is a marker, because that high energy radiation, very tiny amount of it will show up on the screen. And as long as it's not something that hurts you, it's okay. Like when I had half a kidney removed. I had angiomyolipoma, that was bloody muscle, fatty tissue, just these nodules. I probably got one on my arm here, just a knot. I can feel it. It sort of wiggles around. It's a fatty tissue.
It sounds like something about the pimple popping.
Okay. I think this may have been one too. Just the thing here. It's not as fatty feeling, but it just came. This one came after my first or second chemotherapy. That one came after the third or fourth, and they never have gone away. But I don't know, it's been years. But I don't know if it had anything to do with it. That's when they showed up. Okay, but I had half kidney removed, so a little bit more actually, and then they wanted to see if the part that was remaining was functioning. So they put radioactive magnesium. They injected that in my blood so that they could see the kidney removing that and see what the healthy kidney was doing a good job. This one was, even though half or less, it was only doing about a sixth of the job this one was doing. But it had just been traumatized, but it at least was functioning. They said, we're happy with that. So they can use them as a diagnostic thing, and it's not really all that harmful. They just said, drink lots of fluid, you'll flush it out of your system. And it just enabled you to see the operation of the kidney. Whereas any liquid, you wouldn't have seen anything, But with that, it made it obvious. And they could measure it, because they could measure the radiation, with their vision. But, on the other hand, some tumors and stuff, they'll actually plant a little seed of radiation to kill the tumor. And I think seems like they've used radon before with something like that, and other things like that. And that's what they use that for. So that's another medical use. Now, let's get back to the high energy, not nuclear. I forgot this one. That's what X-rays are. high energy radiation that,
Yeah.
see, light won't go through your skin, light won't go through this, but X-rays will, but they won't go through the bone tissue. And actually, sonograms, that sound energy, that can image things because of the reflective, the sort of reflective property. So some tissue will bounce back and others won't. So that's what I mean by reflective, and that's what you're measuring then with that. When I had the angio, when they were first, that doctor I was talking about that saw trace amounts, he was certain I must have bladder cancer. So he had me do a ultrasound, and they did all of my bladder was in great shape. So she just kept looking and found sort of a fuzzy looking something near a kidney and said, well, that could be just about anything. And then they had me go in for a nuclear test. They injected something in my blood, and there, sure enough, they saw the angiomyolipoma. Okay, that's what she was seeing on the ultrasound. Thank you very much. And then that's why they removed half the kidney, because there were bunches of them there which weren't bad, but one was about 4 centimeters. And that was too big. And that could have, if it continued to grow, at some place it could have ruptured. And if it ruptured, there's no way I would have bled out from internal bleeding before they ever could have got me on the operating table. And it made me wonder, because one of my aunts, my father's younger sister, she was older than him, but the younger of the 2 sisters, she was, never seemed to have any health issues or anything. But then one day she suddenly was feeling very chilled, and she called her daughter, and they rushed her to the hospital, and she died before they could do anything. Something had ruptured. They didn't know if it was aneurysm or if it might have been. Once I had mine, I wondered if she had one that was never diagnosed, and that may have been what got her. Hard to say, and I don't think they did an autopsy, so they didn't know. Okay, but anyway, let's get back. What I was talking about was the cubic centimeter, and it started. They took a 100th of a meter, that was a centimeter, okay, and a little cube of that centimeter. They took 1 cubic centimeter of water, because that was the most common material on the surface of the planet, and say, let's call that a gram. So therefore, 1 gram of pure water is always 1 cubic centimeter. So therefore, this can be 1.0000000. You can do as many, because that's how they define what a gram was, is a cubic centimeter of water. So its density is exactly 1.0. Grams per cubic centimeter. If you do kilograms per cubic meter, it's 1,000. I like to use grams per cubic centimeter. Okay. Now, these are your gases, and usually you have to set a certain pressure, because at different pressures, gases expand or contract. So you'd have different amounts. So at 1 atmosphere of pressure, normally it's at a temperature too. They don't really say it here. Usually it's at, here it is, at 0 degrees Celsius or 32. So right at the freezing point, these gases, air. Now remember, I was moving the decimal place 3 places over. This would be 3 places this way, 0.00129. So gases, this is a more reasonable scale. But even hydrogen, look at that. Even on this scale, on the other scale, 0.0000899. That's the lightest gas there is, and that's when they made the first blimps out of hydrogen until the one exploded, okay, and burned like crazy. So then they started using helium, which is the next lightest gas, but notice it's like over twice the density of hydrogen, okay? Right at twice, not quite, no. Pretty close to twice. But these are so much lighter than all the other gases. But those are the thing. Under weight density, you see you have very, very low numbers there too. All right, so that's what density is. And what can we tell from that? Well, anything that's less dense than water This is 1,000 or 1. Like wood, that will float. Ice, that will float. Cork, that will float. If it's more dense than water, it sinks. Alcohol rises over water, except it mixes with water. Gasoline on the top. Oil on the top. Okay? Mercury. And all these things will float in mercury. Lead will float in mercury because mercury is more dense than lead. Amazing but true. Seawater is more dense than water, so therefore you float better. Have you ever been to the beach and noticed you float better than you do in the swimming pool? You do, because seawater is a little denser than fresh water. Okay? And of course, all the gases are light. Oh, but these are important too. If you're in a burning building and you're having trouble breathing, don't get real close to the floor, because more than likely that's going to be carbon dioxide down there. You want to be above the floor, because that, if there's any oxygen still available, that's where it's going to be.
Why do they tell you get low?
Huh?
Why do they tell you to get down? I mean, like, go low.
Okay, well, part of the reason there, if there's toxic materials in the burning, then those are usually lighter. So then you get low. If you smell things that are obviously not good to breathe and you're doing stuff, then you get low. But if it's just, and the other thing is heat rises too, and smoke and stuff, so getting low will stay a little bit cooler. That's probably the main reason. Okay, so those are your density. Okay, have we got time? Yeah, we got time to do a problem or two, an example or two in density. So let's go back to our this. Let me get my color back. Okay. Find the weight density of a block of wood, 3.00 inches. It's a block of wood by 4.00 inches by 5.00 inches. Okay. With a weight of 0.700 pounds. So the F sub W is 0.700 pounds. That is a force, a weight. Okay? Now, they drew the piece of wood. I'll sort of try to. This. Let me get my bearings right here. This. I can't get it right. Came down too far. Okay. Anyway, a block of wood here. This is really ugly. Okay, something like that. Block of wood. Not a very pretty block of wood. Okay. 3 inches by 4 inches by 5 inches, or something like that. Okay? Now, what do you need to have weight density? Remember, they call that D sub W. What is that formula? F sub W, that's the weight over volume. Okay. Now, this is going to give you the volume in cubic inches. Inches times inches times inches. So that's 4 times 5 is 20 times 3 is 60.0 cubic inches. And you do 0.700 pounds per 60.0 cubic inches. And that's going to give you a very small number. Why is it much smaller than the one in the book? Because in the book, they give this in pounds per cubic foot. So that means you got to do a conversion. Now, you can go to the tables in the back, or you can do it this way. Multiply it by blank blank equal to blank cubic feet. Okay, what unit? Always put the units in the place. What unit goes where? You're in between feet and inches. What unit goes where? One on top, one on bottom. Inches on the bottom, excellent. And feet on top. And then how many inches in a foot or feet in an inch? 12 inches, 1 foot. But you're not dealing with inches and feet, you're dealing with cubic inches and cubic feet. So you're going to have to cube this, cube that, cube this, but you've also got to cube that. I can cube 1, that's 1. I can cube feet, that's cubic feet, cubic inch. Those are easy. 12 cubed is, someone punch that in on a calculator, see what you get. A pretty big number. Anybody? Okay, I know y'all are working by paper. That's tough, but you can do it. What is 12 cubed? Have you got it on your calculator yet? Say again, 1,700 what? 28? Okay, that sounds reasonable. Cubic feet. Wait, that's cubic inches. So divide 60 by that number, 1,728. Because the cubic inches go out, and that'll give you cubic feet. Pretty smart. Okay, say again, 0.0347. Okay. So that's how many cubic feet we have. So that's what we do, 0.700 pounds divided by 0.0347 cubic feet. And that should give you a number about 20 something. Anyone get it? 0.7 divided by 0.0347.
20.17.
And that would be, well, wait, we only have 3 significant digits everywhere, so let's round that to 20.2. 1, 2, 3 digits, look to the right, it's more than 5. 20.2 pounds per cubic foot. Okay, let's go back to the table in the book and see what wood was. 26. We got 20.2, so this must be a lighter piece of wood than that was. Okay, let's see what they got in the book. 20.2, good for them. All right, does that make sense? Now, just for funsies, in case you don't want to use the train track method or whatever I just used, let me show you how to do this from the back of the book. That appendix that we talked about, this was a volume conversion, so it's conversion table for volumes. And by the way, your weight and mass density was that table 12, the same one we just saw in the book. Okay? Volume is at the top of page 687. That's table 4, conversion table for volume. It said cubic feet to cubic inch. Okay, they did it one way. Let's do cubic inch to cubic feet. There it is. Oh, we did. Oh, no. Let's go back. Cubic feet to cubic inch. Cubic feet to cubic inches. There's that 1,728 was right there. Okay, so if you're going from cubic inches, which we had 60, to cubic feet, multiply, so do this on your calculator. 60 times, okay, now get your units right, your place right, 5.79 EE negative 4. 5.79, okay, write down 60 times 5.79 EE negative 4. That's from your back of your book. Seven nine.
0.03474.
Look at that. That's exactly what we got. So if you didn't want to do the train track method like we did in cubing and stuff like this, you can go to the table and use that. But to go from the unit that's on the left, we started with cubic inches, then you multiply by what's under the column, cubic feet. So if you want to do it that way, you can. All right.
Okay.
Good deal. Let me get marked where we left off. We did example 1. We got that right. We still have to do example 2. So we'll begin there next time.
7
Okay.
examples in the book.
What's that?
7 examples in the book.
Yeah, and this is in section, goodness, what is it? I wish they labeled this at the top. 12.5, density. Okay, and once we finish 12.5, which we're at the end. So next time I'll try to have your test ready for you for chapter 12.
12, that'll be test 3. We got 6 tests, right?
What's that?
6 tests.
I'm guessing about that.
Yeah, I think we got 6.
All right. All right, good deal. Any last questions? Okay.